We know that one of the biggest problems for the linear regression model is endogenous explanatory variables. We know that if the explanatory variables are endogenous, then the OLS estimator will not be unbiased and it's not going to be consistent. So the purpose of this lecture is to present the three most common cases where we have endogenous explanatory variables working with a random sample. So the first case is the missing variable problem. So let's call that example 1. The true model is that the expected value of y conditionally on three explanatory variables x2, x3 and x4 is indeed a linear function of these variables. However, we incorrectly assume that the conditional expectation depends on only x2 and x3, so we make the following assumption. With this assumption, we run the linear regression model where y is equal to this conditional expectation plus an error term, and we estimate this model using OLS. Then the following will be true. If any of my included variables, x2 or x3, is correlated with the missing variable, the one I'm not including, x4, then this variable, x2 or x3 or both, it will be endogenous. The reason is simply that the error term of our specification will include the x4 explanatory variable. And if x2, for example, is correlated with x4, it will also be correlated with the error term. If I estimate this model using OLS, and I estimate beta 2, for example, with B2, then B2 will be a biased and inconsistent estimator of the marginal effect of x2 on y, here interpreted as keeping x3 and x4 constant. However, in the case that all included variable, or let's say in the case that I have an included variable that's independent of the missing one, then that variable will be exogenous. So it might very well be that, for example, x2 is exogenous while x3 is endogenous. But keep in mind, it's enough that one of the explanatory variables is endogenous to ruin OLS estimates for all parameters. The second case, where we often end up with the endogeneity problems, is the case of simultaneity. So the idea here is that I specify a linear regression model, but I have a simultaneity problem with at least one of the explanatory variables. That means that not only does this explanatory variable affect my y variable, but the opposite may be true as well. That is, the explanatory variable may be explained by the dependent variable. So in this case, these two variables are then endogenous and they are actually determined jointly from two specifications. One specifying the first y1 and the second model explaining the second dependent variable. So in my first equation, I have an exogenous x variable, but my second explanatory variable, y2, for that one, I have a simultaneity problem. Not only is y1 determined by y2, but y2 is also determined by y1. So the problem here is that when we consider the first equation, the one determining y1, then y2 will in general be endogenous. The reason for this is that y1 and y2 will both be correlated with both of the error terms, both epsilon I and nu I. and that will make y2 correlated with epsilon I in the first model, therefore endogenous. The third case is the case where we have measurement errors in an explanatory variable. So a simple illustration of that would be, I have a true model where the conditional expectation of y given z variables and x variables. Z variables are the true variables that we do not observe, and x variables are the measurements of the z variables. If in the true model the conditional expectation of y depends on the z variables, the true values, and I observe the x variables and use them in the regression, then the x variables will be endogenous. So in this case, for example, xi2, the second x variable, the x variable with the subscript 2, that's a measurement of zi2. And x3 is a measurement of the true z3. Since I don't observe the true variables x2 and x3, only the measurements of those, I run a regression of y on x2 and x3. Now, any variable that has measurement errors will be endogenous. If x2, for example, is correctly measured or a correct measurement of z2, then x2 will not be endogenous. However, if x2 has measurement errors, it will be endogenous. So all variables that are free of measurement errors, those variables will be exogenous.